Okay, for what we have in 25, okay, we're looking at compound interest. And in what we have for part A, okay, it says to find the future value of $3,000 invested at 10% compounded monthly after 6 years. Okay, so for non-continuous compounding, this is the future value formula. Okay, and we're looking at solving for A, and for the components we have here, P is in reference to the present value, which we have at $3,000. And we have for 1 plus r over n, r refers to the rate of interest, which we will record as a non-percent decimal. So 10% becomes 0.10, and n is the compounding frequency, so this will be monthly, and the time span we have for 6 years. Okay, and if we fill in the values, okay, so we have, again, so P is at $3,000. You have times quantity, 1 plus r over n, so you have 1 plus 0.10 over 12, and we have to the n times t, so we're looking at raising to the 12 times 6, and looking at what we have at this juncture. Okay, so we have $3,000, and for 0.10 over 12 added to 1, okay, and so we have what's going to be a continuously running decimal, so you have 1.008333. If you keep this sum, and we have raised to the 72nd power, okay, so this decimal, when raised to the 72nd degree, okay, you have a number that's a little bit over 1.8, so you have 1.81759, and some decimal places after that, and multiplied by 3,000. Okay, so after 6 years, the amount of $3,000 under the conditions will grow to about $5,452.78. Okay. Now, in the case of what we have for part B, okay, we have same quoted values, but the difference this time around is where we have continuous compounding. So if I take what I have here and run it through the perspective of continuous compounding, okay, so this is going to be the formula. We have P times E to the R times T. Okay, so P is still at $3,000. We have E to the R times T. Now R, again, we have at 0.10. Time span we have for 6 years. And 0.10 times 6 is going to be 0.60. Okay. And so for what we have in this case, all right, so we have for E to the 0.6, (1.822, 1188, and so on, and multiplying by $3,000. Okay, so the future value, okay, we have about, okay, between $13 and $14 more in comparison, where we have about $5,466.36. Okay, for what we have in number 26, now we're looking at essentially an amalgamated form of the future value formula, and we're crossing over to annuities. Now we have in 26, okay, we have Ray who plans to retire in 15 years. He contributes $1,000 to an IRA semi-annually. The rate of return is assumed to be 10% compounded semi-annually. Okay, so for the annuities, we're looking at where the compounding of interest and the deposits are going to be at the same frequency. Now, in part A, it's asking what would be the minimum value of the IRA after 15 years when Ray retires. Okay, that is if Ray had invested at the end of each 6-month cycle. So for for the minimum, okay, you have your annuity formula. Okay, and this is the formula. It looks almost like the future value formula in compound interest, but here we're looking at recurring deposits. Okay, so we have P is what Ray is putting in. We have the rate of interest at 10%, and again, R we have recorded at 0.10. We have semi-annual compounding as well as deposits. Okay, so N is equal to 2, so we have twice a year. And again, the time span will be for 15 years. So in looking for what we have in the future value, okay, so we're looking at $1,000. We have times the quantity, okay, so you have 1 plus 0.10, and we have over 2, and we have the 2 times 15 degree. We have minus 1, and we have times N over R, so you have times 2 over 0.10. And in the case of what we have here, so you got $1,000. We have times the quantity. Now we have for the sum in parentheses. Now we have 1.05. And this will be to the 30th degree. And we have minus 1. And we have 2 divided by 0.10, so that is going to be at 20. And for what we have in the case of 1.05 to the 30th, okay, and we're going to have, in this case, so you're going to have, okay, number that's going to be just over 4.32, and I'm going to take 1 away, and for what we have in the setup, so we have $1,000. Now for 1.05 to the 30th, minus 1. Now just go ahead and give you the full decimal display. So you have 3.32194237.5. We have multiplied by 20. So altogether, so you have $1,000. You have times the difference. And again, we have times 20. So for the future value in this case, okay, we're looking right at $66,438.85. Now for part B, it's asking for Ray, what would be the maximum value if Ray retired, okay, should he had invested at the start of each 6-month cycle. Okay, so if Ray had invested at the start of each 6-month cycle, so we're looking at the theoretical maximum. Okay, so for part B, there's going to be the slightest modification, and we have here, okay, that at the start of each cycle, okay, now you got your annuity formula, but there's going to be the slightest difference, and that's going to be where we have times the quantity of 1 plus R over N. Now, again, without this particular item, you got your minimum. And again, we had this to be at $66,438.85, and for the future value, had Ray been investing at the start of each cycle, you got this amount times 1 plus 0.10 divided by 2. Okay, so you have $66,438.85. That's the minimum, in other words, from part A. But now, in terms of the maximum, you'll be looking at another 5% that will be applied. Okay, and so we're looking at, in this particular case, okay, you have for the maximum. Okay, so for Ray, you're looking at, after 15 years, about $69,760.79. Okay, for number 27, okay, we have for a child born this year, a 4-year college education at a public university is projected to be roughly $170,000. Assuming a 5% rate of return compounded monthly, about how much must be contributed to a college fund every month in order to have $170,000 in 18 years? And it says to use the regular annuity formula, and it says you are solving for P, the monthly amount, okay, that will be applied. And it says to round up to the next penny not necessarily the nearest penny, but to the next penny. All right. So we have in 27, we're looking at solving for P. Now again, the goal is $170,000, okay, which is projected into the future. Now the time span is going to be for 18 years. In the frequency of the deposits as well as the compounding of interest, okay, this will be on a monthly basis, so N is equal to 12. And the rate of interest we're going to have at 5%. Okay, and just taking what we have with the numbers, okay, so you have the future value A. So we have at 170,000. We have is equal to P. We have times the quantity. We have 1 plus R over N, so you have 0.05 over 12. We have to the 12 times 18 degree minus 1. And we have times N over R, so N is at 12. We have R at 0.05. So 170,000 we have equal to P. And we have for 1 plus 0.05 over 12. Okay, so you have 1.00416. And the 6's will repeat. And again, we have to the 12 times 18, so this will be to the 216th degree. You have minus 1. 12 divided by 0.05, okay, that would be 240. So 170,000. And we have equal to P. Yeah, so you have, for this number, you have about 2.4550, take away 1, you have times 240. So you have P times 1.455008, and you're going to multiply by 240, and just putting the full decimal display. So taking this difference and multiplying by 240. Okay, so you got 170,000 is equal to 349.2020215 P, and then dividing into 170,000. Okay, now we have for P, you have 486.8242, and again, rounding up to the nearest penny. So rounding up turns out that for about how much must be put in every month to have at least $170,000 after 18 years. So we're looking at the future value, or I should say the present value, in order to get to the future amount of 170 grand. Okay, we're looking at $486.83 a month.